Hello everyone. Welcome to the tutorial session for the NPTEL course of Secure Computation Part 2. I am Sayani Sinha. I am a research scholar at IIT Kharagpur and I will be taking your weekly tutorial session for 2 hours every Saturday from 6 pm to 8 pm. So you can feel free to join and be a part of the discussion that we are going to do in this tutorial session. And also basically what I will do in this tutorial session is that I will first do a quick recap of the particular week's content with whatever is provided in the professor's lecture series, and then we can discuss the problems given in the weekly assignment on the NPTEL website for this course. So so for this week, actually, as you know that the assignments are already posted for week 1 and the submission deadline is later. So basically before the submission deadline I will not discuss the exact questions of the website, but I will try to give the idea on how to solve those problems. And then once the submission deadline is over for a week's assignment, then in the next week we can discuss and go over those exact problems given in the weekly assignments. Okay, so let me share my screen. I will be writing in the PowerPoint and try to explain the first week's content, which is mostly over Byzantine agreement, a perfectly secure protocol for Byzantine agreement. So let me start with that. I hope my screen is visible. Okay, so this is week 1 and let us get started. So basically these are the highlights of this week's topics. Okay. So we start with the brief discussion. So I expect that whoever are joining in this tutorial session, they are already acquainted with the actual lectures that are presented on NPTEL website, lectures given by professor, and then you can join this tutorial session to clear if you have some doubts, and we will also, as I said, that go over the weekly assignment questions. So for this week, as we are not able to discuss exactly on these problems of week 1 because the submission deadline is not yet over, so I just go over the basic topics that are there in the week 1 lectures. So starting with Byzantine agreement, then reliable broadcast and various adversarial power in different security settings, conversion between Byzantine agreement and reliable broadcast, and then comes the main interesting topic of perfectly secure Byzantine protocol, which is EIG protocol, exponential information gathering protocol. So we will see the EIG data structure and the demonstration of how EIG works. Okay, so let us get started. So so what is Byzantine Agreement Protocol, right? So there will be multiple parties. Let us write it P1, P2, P3. Let's say there are 5 parties. Okay. Then usually we denote with N, total number of parties, right? Total parties. And we denote with small t, number of corrupted parties. So when we say corrupted, basically Byzantine Agreement Protocol is discussed in the malicious setting. There, if one party is corrupted, that party can arbitrarily deviate from the protocol. So whenever we talk about any cryptographic protocol, so usually we talk about two different adversarial setting. One is semi-honest or passive setting and another is malicious setting. In passive setting, the adversary or corrupt party cannot deviate from the protocol. It can basically it can see the transcript. Transcript means whatever is coming to that party or going out of that party, all the computations. So that from that transcript it can try to derive some secret information about other party's input, but otherwise it will execute the protocol as defined in the protocol. So it will not deviate from the protocol. That is passive adversary or semi-honest party. But in case of malicious setting, a maliciously corrupted party can arbitrarily deviate from the protocol. So let's say the one party which is corrupted, if it is supposed to send a value 5 to some other party, it may choose to send any value other than 5, or it can send 5 as well, but it can deviate arbitrarily, or it may even choose not to send anything at all to the party. Okay, so it can arbitrarily deviate from the protocol. Now also, if it is supposed to run some algorithm, it can choose not to run the algorithmic step as it is defined, right? So that is what we call malicious party, maliciously corrupted party, right? Now in case of Byzantine agreement, there will be total n number of parties. Out of them we allow at most t number of parties to be maliciously corrupted, and at the end of the protocol what we expect is that even in presence of these maliciously corrupted at most t number of parties, all the honest party among these n parties will have a common output at the end of the protocol, right? So you may wonder, why do we need this? Okay, let's say what I am trying to say, let's say P1 has its input x1, P2 has its input x2, P3 has x3, P4 has x4, P5 has x5, and among them let's say P4 is a corrupt party. Okay, so it may not send x4 to everyone. Okay, so if these parties actually want to agree upon some common value, it may be the case that P1, P5 and P2, all of them actually have same input, but they don't know each other's input, right? In the beginning of the protocol, no one is aware of other parties' input. They are only aware of only its own input. Now what happens that at the end of the protocol they expect to agree upon some common value x star. So if P1, P2, P3 and P5 are honest, then we expect that all of these 4 honest party will agree upon this common value x star. Now this x star can be any one value out of this x1, x2, x3, x4 or x5, or it can be anything else as well. Okay, that we will see in detail, but the only thing we essentially want to ensure is that this x star should be consistent over all the honest parties, right? Okay, now you may wonder that why do we need this. So let's talk about some real world scenario, not going into details of cryptography or multi-party computation. So in a very rough example, don't take it too I mean, it is not as it is some example, but a rough analog. So let's talk about some examination is going on, right? In school you used to like in the exam you have computed some problem, and you have got some solution. Now you may want to match with your friend's result, right? Whether he or she has also got the same solution to that problem. So you want to check the value, mathematical value, let's say. Okay, now you will be convinced that you have actually calculated a correct value if four of your other friends also have obtained the same value. Then it is highly probable that you have correctly computed the sum, right? Now let's say you have a group of friends, group of five friends. Then let's say one of them, maybe he or she is the topper, so he or she does not want that you actually also get the good marks, so he or she is trying to cheat. So actually maybe he has got the answer to, let's say, 150, but he is trying to say that no, my actual result is 100. Okay, so I got 100 as the result. Now yeah, so in that case we can say that that particular friend who is trying to cheat others, saying a wrong output of the problem, he is the malicious party. Okay, now still you want to be convinced that others who have got the same output, so you might want to run a protocol. So no one will be declaring what solution he or she got from the problem, but still it will run, some protocol will be executed, and at the end of the protocol the solution that comes out will be the correct solution indeed. So that is a very rough example of some agreement, right, where you want to reach to a consensus in a distributed manner. Okay, so coming to the nitty-gritty of these details, right? So the Byzantine agreement protocol must ensure three security properties. First is termination, right? Termination or liveness ensures that the protocol must end after a finite amount of time, right? So no process can run infinitely, right? So that's why termination is necessary. And then comes the consistency property that I am talking about. So if P4 is corrupted party, then we say that at the end of the protocol, P1, P2, P3 and P5, they should agree upon some common output value X star. Okay, and then comes validity property. Validity property says that if at the beginning of the protocol all the honest parties are starting the protocol with same value, okay, so if P1, P2, P3 and P5 has some value X, all of them have the value X at the beginning of the protocol, then at the end of the protocol X star should be exactly equal to X. That is ensured by validity property. Okay. Okay, and then comes the reliable broadcast protocol. Okay, so in reliable broadcast, basically there are also again n number of parties, but there will be one single designated sender, right? So let's say P2 is the, or I mean this is P1, is P2. So let's say P2 is the sender. In Byzantine agreement, everyone is equal, right? No one is a particular sender. Everyone has some input and they want to agree upon some particular value at the end of the protocol. So all of them should have a common output, all honest parties, of course. But in reliable broadcast, one party is the sender and he will broadcast to all the other parties, other n-1 parties, but we want that broadcast to be reliable, which means that even if among these n number of parties, t number of parties are maliciously corrupted, which may even include the sender itself. So sender also can be corrupted, okay. And in that case, what happens? Let's say P2 has the value x to send. Now P2 actually sends x to P1, some x dash, some other value x dash to P5, x double dash to P4, x triple dash to P3. Completely arbitrary value it can send to all the parties. That will not be reliable because everyone will receive from P2 different values. So that is not a reliable broadcast. In reliable broadcast, at the end of the protocol, even if sender itself is corrupted, every honest party will receive a common output value, right? So sender can be corrupted, sender can be honest. If sender is honest, then whatever value sender wants to broadcast to other parties, at the end of the reliable broadcast protocol, all the honest party will receive that value only. That is the validity property of RB protocol. Just like BA, in BA we said that if all the honest parties are starting with same input value, then at the end of the protocol the common output that they agree upon will be that common input value only. Otherwise it will be consistent. Otherwise, if the honest parties were not starting with same values, they may have starting with different values, then they all will agree upon some fixed value that will be common at the end of the output, that is consistency. But if they are starting with same value, then at the end of the protocol the output will be that value only, that is validity property. In case of RB also, reliable broadcast also, these three properties should be there: termination, consistency and validity. So termination is again saying that the RB protocol should not run for infinite time. It should be completed after a finite amount of time, should be terminated. And consistency of RB protocol is again that all the honest party should receive a common output, right? So they will perceive it as the value broadcasted from the sender P2, but P2 can be effectively corrupted party, but still all the honest party should receive same common value, right, after the broadcast protocol is executed. And if sender is honest, then whatever value it actually wants to broadcast, that value will be the output of RB protocol for all the honest parties, right? I hope that makes sense. Now once we have introduced the RB and BA protocol, so you may understand, right, that this BA and RB, they are actually kind of basic building block for a multi-party secure computation. So you are trying to compute some function in a multi-party setting, but let's say after the computation is done, each party has received some output of that computation. Now all the parties want to ensure that they have indeed received the same value, right? In that case they may want to run a Byzantine agreement protocol. I am just roughly speaking of some possible application, otherwise it will of course receive several applications throughout the course. Okay, now now we will see that this Byzantine agreement protocol and reliable broadcast protocol can be converted from one to the another, right? They are convertible to each other. How? So let's say you have a secure Byzantine agreement protocol. Okay, you have this, so let's denote the protocol with pi subscript with BA. So this is the protocol that you have. Now with this protocol in hand, you want to design a reliable broadcast protocol. So as you know, in reliable broadcast protocol there must be one designated sender. So what happens is that in that case, the designated with pi BA in hand, how you execute pi RB, right? So for that, at first you allow that designated sender of your reliable broadcast protocol to just broadcast its value to all the other parties, right? So there are n parties, among them one is sender, so that sender will send its value to all the n-1 other parties, right? Now there is no yet no reliability context here, right? It is just plain broadcasting, it may not be reliable. So if we consider the example of 5 parties, okay, let's say P3 is the sender and it has some value V to send to others. So it may send to all the other parties V only, or it may send some other values also. Let's say it sends to P1 V dash, but to others it sends P. It might be the case if P3 is corrupted. Otherwise, if it is honest, it will of course send the same value to all the other parties. It will not lie about its own input, right? Now whatever it is, so the first step of this pi RB protocol is just a broadcast by P3, the sender party. No reliability is yet involved here. Now once this is done, so each of the party now have its own input, right? So P1, P2, P3, P4, P5, all of them have some input to it, right? So P1 has P, P2 has P dash, P3 has P, P4 has P, P5 has P. Now they will run a Byzantine agreement protocol that you already have with you, with these values as their input to Byzantine agreement protocol. So as you know, in Byzantine agreement protocol, all the parties start with their own input, but in RB protocol only one party has some input and it wants to broadcast to other parties. So because we have Byzantine agreement protocol, which is malicious corruption, which is secure against malicious corruption, with that at hand, how we design the RB protocol? We first allow the designated sender to broadcast its value to all the other parties, and this broadcast will be actually reliable only if that designated sender is honest. Otherwise, it will make other parties receive some different values. Whatever is the case, each party will now receive some value, V, V dash or anything, after the first step. And now in the second step, all the parties with their own input will run the pi BA protocol that is there in our hand. And at the end of the pi BA protocol, as we know, by the consistency of pi BA protocol, all the honest party will receive a common output of this protocol. So that is what we also require in RB protocol also, that at the end of the protocol all the honest party will have the same output, and that is what happens here also. So at the end of the second step, after running the pi BA protocol, all the honest party actually receives the common output. So we have achieved pi RB by using pi BA. And of course the termination, consistency and validity are satisfied. How? Termination will be satisfied because this is nothing but a plain broadcast protocol which may take some particular amount of time, say T1. And the second step is pi BA protocol, for which we already know, since it is a valid pi BA protocol, it must have the termination property, so it will be terminated after some finite time, say T2. So overall our pi RB protocol using pi BA, that will require some T1 plus T2 amount of time, which is again finite, so termination protocol is satisfied. And consistency is also satisfied because, as I said, by the consistency of pi BA protocol, at the end of the second step all the honest party will have the same output. So yes, consistency of RB protocol is satisfied by the consistency of the underlying BA protocol. and validity is also satisfied, because if so in validity of RB, what we said, in a reliable broadcast protocol, if the sender is honest, then whatever value the sender is wants to broadcast to all the other parties, that is the value which will be actually received at the end of the RB protocol by all the honest parties. Now here, if the sender P3 was honest, then it will send the values V to every other party, right? And then if the BA protocol is getting started with the same input V by all the honest party, then the output will also remain V for all the honest parties. That is by validity of the BA protocol. So by validity of the underlying BA protocol, validity of this RB protocol is also satisfied. And this requires just some T less than N. So corruption, number of corrupted parties should be less than number of total parties. That is the only requirement in this case. However, in the reverse direction, I mean, if you have a pi RB protocol with you and using that you want to design a pi BA protocol, in that case, how do you do it? So now the first step is that every party, so as you know, pi BA protocol is in that case every party has some individual input to it, right? But in RB, you can only allow one party to be the sender and broadcast reliably. So to have a Byzantine agreement protocol from reliable broadcast protocol, you actually can consider each of the parties present in the scenario. So again, if we consider 5 parties, okay, each of them will have some input with it, say V1, V2, V3, V4 and V5. Okay, now each of them will individually run a reliable broadcast protocol to broadcast their value to all the other parties, right? So 5 instances of pi RB will be executed in the first step. So that execution can be parallel. P1 will start a pi RB protocol with its input V1, P2 will start a pi RB protocol with its input V2. For each of such RB protocol, basically at the end of all 5 RB protocol instances, each of the party will have basically 5 inputs to it, right? So P1 will receive an array of 5 values received from itself, that is its own input, and received from other parties. Now it can be the case that some of them can be corrupted, right? So let's say P2 is the corrupted party here. So after the reliable broadcast protocol executed by P2, all the honest party will of course agree upon some common values, but it may not be V2. So let's say it is some V2 dash, but V3 is honest. So by the validity of RB protocol, V3 will be received as it is, V4 will be received as it is, V5 also will be received as it is. P2 is also honest, right? P2 is also honest. So it will receive, I assume this is to be corrupted, right? This is the corrupted party. So P2 is corrupted, but it will receive let's say V1 only from P1, like as by the RB protocol executed by P1, it may receive V1, but it may not reveal it as V1. It can say that okay, my output is V1 dashed. So you cannot guarantee how the corrupted party behaves. So it can be anything arbitrary, right? And we don't care about its output as well, because whenever we say about the output of BA protocol or RB protocol, we say that honest parties will have the consistent output. We cannot guarantee about the dishonest parties, right? Anyway, so some value it will receive, again 5 number of values. For P3, since V1 is honest, this value will match. V2 is corrupted, so it will not be exactly V2, but it will be consistent with P1's output, right? V3, V4, V5. Similarly, P4 will also have this. Now, what happens is that we say that once such n number of values are available to each party, as the output of BA protocol, they will actually output majority of this 5 values. Okay, everyone will output majority of these 5 values. Now, one thing to notice is that if let's say the consistency is by default satisfied, right, by the consistency of RB protocol. Okay, and what about the validity? For validity, if you're at the starting of BA protocol, all the honest party will have the same input, okay, then we should receive the same output. So in this majority voting, actually that particular output should be higher in number than corrupted outputs, right? So that will be ensured only if your n minus t, that is at least n minus t honest party will be there. So number of honest parties should be greater than number of corrupted parties. Only then this majority voting will give you a the output which is expected, with which all the honest parties started with the protocol, right, to ensure the validity property. So for that, actually you need n to be greater than 2t, or in other words t to be less than n by 2. Only then, having a reliable broadcast protocol, you can achieve a Byzantine agreement protocol. Okay, now let us move to EIG protocol, right? So that is the main protocol that is there in this week's content. So we will just we will directly go to the demonstration of EIG protocol without going into too much detail of the algorithmic step. You will find the algorithmic step in the lecture, but I will try to keep it in a way so that you can get another interpretation of the protocol run. Okay, so what is EIG? So EIG is exponential information gathering, right? This is a protocol which is perfectly secure. What do we mean by a perfectly secure protocol? Basically, the adversary or the corrupted parties will have unbounded computational power, and all the security property, right, the termination, validity and consistency, all these properties actually will be satisfied with probability 1, right? That is so that means with probability 1 always the output of the protocol will be consistent, with probability 1 always the output of the protocol will be valid, and with probability 1 always the protocol will terminate in a finite amount of time. So, and even if all these will occur even if the T maliciously corrupted parties have unbounded computational power. So that is what we mean by perfectly secure protocol. And EIG protocol, we are trying to now see EIG protocol for Byzantine agreement here. So this is the first perfectly secure protocol for Byzantine agreement. Although it is very inefficient, as you can guess from the name, it says exponential information gathering. So maybe each party needs to store exponential amount of information or may need exponential amount of communication between each other to achieve the protocol. So that is practically inefficient, but still it is of very it has its own importance because it is the first Byzantine protocol to achieve Byzantine agreement, right? Okay, now I will start directly with demonstration of a protocol, but before that I must mention about the tree data structure used in the EIG protocol. So EIG tree data structure, so important points about EIG tree data structure is this. Let's say N is again total number of parties, right? Total number of parties. T is corrupted number of corrupted parties, okay, and now each party who are participating in the protocol will have to store a tree data structure with itself. So they will locally store a tree. Let's denote the tree with T subscript with N comma T. So a tree will be stored by each party locally, okay. So we start with N equal to 4, T equal to 1, and for EIG protocol remember that N must be greater than 3T, okay. N must be greater than 3T. So here you can see that 4 is greater than 3 into 1, right? Okay, so in our case we need to see the shape of T4,1 tree. So for any N, T EIG tree, there must be T plus 2 number of levels of the tree, okay, levels, and we usually start the level index starting with index 0, okay. So level 0, level 1, like that, starting with index 0 from top to bottom. So that is root of the tree is at level 0, okay. T plus 2 levels, and each node at level say I, okay, each node at level I will have N minus I number of children. So with this much information you can guess the structure of the tree. If we try to draw T4,1, so root node is at level 0, okay, this is level 0. So how many children it will have? So level 0 node will have N minus 0, that is 4 minus 0, 4 children. So let's draw 4 children. 1, 2, 3, 4. They are level 1 nodes. And how many children each node at level 1 will have? That is, if level is 1, then number of children is 4 minus 1, that is 3. So each of these nodes will have 3 children. Now how many levels we have? Level 1, level 2, level 3, right? And the first point says that t n comma t has t plus 2 level. T is 1 for our case, so there will be 3 levels, and we have already drawn 3 levels. So this is what our t4 comma 1 will look like according to these 2 points. Okay. Now next point is that each node, right, at level I will have a tag or label, right, of length I. Okay, if the node is at level I, its tag will have a length I, and the tag consists of I distinct party IDs. Okay. So we will see how the leveling is done. So we start with node at level 0. So level 0 node will have a tag of length 0. So 0 length string, let's denote it with lambda. So this is some, you can consider it as a empty tag, okay, denoted with a special notation lambda. So it does not have any length actually. Okay, good. Now at level 1, so we know each node at level 1 will have a label of length 1, and this will be distinct. So let's say this is party ID. So party ID are like, we have P1, P2, P3, P4, 4 participating parties, right? Total number of parties is 4. So let's denote the parties as P1, P2, P3, P4, and 1, 2, 3, 4 are the party IDs. So each node at level 1 will have distinct party IDs. So okay, so this is 1 party, the level is 1 of this node. This node has level 2, level 3, label or tag, you can say. So all these nodes have tag of length 1 and they are distinct. Okay, now coming to next level, so each of them will have a tag of length 2. So I am writing them as 1 2, 1 3, 1 4. Length 2, each of them has length 2, and each tag consists of I distinct party ID. So there cannot be a label or tag of the form 1 1, because then 1 is repeated, but we need both the party IDs present in this 2 length tag to be distinct. So 1 2 is allowed, 1 3 is allowed, 1 4 is allowed, but 1 1 is not allowed, or 2 2 3 3 4 4, they are not allowed. So let's write the tag of these nodes as 2 1, 2 3, 2 4. This is 3 1, 3 2, 3 4. This is 4 1, 4 2, 4 3. And the last property is also that each path, right, from root to leaf. So as you know, for tree this is the root, and the last level nodes are leaf nodes, right? They don't have any children. So any path from root to leaf, since the tree has level t plus 2, so you can easily see that the length of path is t plus 1 actually, right? 1 2. So that is t is 1 and 1 plus 1 is 2. T plus 1 length path are there for each path from root to leaf, and this each path from root to leaf has actually t plus 1 distinct party IDs on it. For example, if I consider say if I consider this path, okay, so this path has 2 and 1, right? 2, 2, 1, so total 2 and 1, these two party IDs are there, they are distinct party IDs. So t plus 1 is 2, so you can say that two distinct party IDs are there through this path. If we take some other path, let's say this path, then this path has 3 and 2 as their distinct party IDs through this path from root to leaf, like that. Okay, so these are the properties that this EIG tree data structure should satisfy. With this information with us, let us proceed to how the EIG Byzantine Agreement Protocol works. Basically, very roughly speaking, at each level, every node will pass the information of its previous level node's tag and value to every other nodes, even including itself. So let us see it with an example. So I am going to next slide. Once we have the clear view of the EIG tree data structure, let us move to the actual EIG protocol execution. So I will quickly draw the EIG tree for total n number of parties and t number of corruption. So this is level 0, level 1, level 2. Level 0 node should have n minus 0, that is, so in our case we are considering n equal to 4, t equal to 1. Party IDs are P1, P2, P3, P4, and we will look at a bit agreement protocol. Bit Byzantine agreement protocol, because we are trying to agree upon a common bit over all the honest parties. So they will start with a bit input. Input can be anything, so we will later see what to do if we have different or like larger length input, but for now we start with a bit agreement protocol. So each of the parties will have some initial bit values. Let's say this, they are the initial input bit values and they want to reach to some consensus. Okay, and let's say our P4 is the corrupted party, let's assume. Okay, let me just keep a red color for corrupted to remember that this is corrupted, and corrupted party can behave arbitrarily, right? Okay, and to give the labels, so this has label 1, label or tag I can say, tag 1, tag 2, tag 3, tag 4, tag 1 2, tag 1 3, tag 1 4, 2 1, 2 3, 2 4, 3 1, 3 2, 3 4, 4 1, 4 2, 4 3, right? Okay, now so since I said that each party will have its local copy of this tree data structure, right, that, and they will gradually fill up all the nodes of their local tree with some value, taking a top down approach. So it will start filling up the tree values with the root node and gradually reach the allocation of values to leaf nodes. And once the whole tree is populated for all the parties local copy, then they will take a bottom up approach to get some new value to the root node, and that new value at the root node will be the final output of Byzantine increment protocol. Okay, so to see the to represent local copies, right? So I have basically okay, just so, I have 4 parties: P1, P2, P3 and P4, and each of them has their local copy of EIG tree, and EIG tree nodes are these, right? Lambda, the labels. So I will assign value through the running of the algorithm. Okay, there is node with level 2, node with level 3, level 4, level 1, 2, 1, 3, so we have 1, 2, 1, 3, 1, 4. We have 2, 1, 2, 3, 2, 4, right? We have 3, 1, 3, 2, 3, 4, 4, 1, 4, 2 and 4, 3. So I wrote this because each of the party have these node labels to its local EIG tree, and it will gradually allocate the values to there. So if you just follow that this is level 0 node, these are level 1 nodes, and all of them are level 2 nodes. Okay, so how the values are assigned to these nodes, let's see that. So the protocol will run for t plus 1 rounds. So what happens, so first actually let's start with initialization phase, and after initialization there will be t plus 1 number of rounds. So in our case t is 2, so 2 rounds will be there. But before that, let's start with initialization. So what happens in initialization? In initialization, each party will assign their own input value to the root node of their local copy of EIG tree. So each of P1, P2, P3, P4 has their local copy of EIG tree. So they will assign, first I am writing here, so P1 will assign value 1 to root node. Value 1, why? Because the starting input of P1 was 1, right? P2 will assign value 0 to root node. Okay. Likewise, P3 will assign value 0, root node of its local copy of EIG tree, remember, and P4 will assign 1. So since P4 is actually corrupt party, so it may choose to assign 1 or 0. So it can, as I said, it can arbitrarily choose to report any value, right? Although it is supposed to say 1, but it may not, because it is a maliciously corrupted party. So for now, let's assume it is actually assigning 1 to its own root node. So that is only part of initialization phase, right? So following that, if I write the values here, so P1 has assigned, so root node is nothing but the node with level lambda. So P1 has assigned value 1 to its lambda node, P2 has assigned 0, P3 has assigned 0, P4 has assigned 1. So level 0 of all the parties local EIG tree is initialized in the initialization phase. This is done. Okay. Now comes round 1. So round 1 will basically have its send operation, receive. So each party will send something, each party will receive something, and then they will assign values to their nodes at level 1. At the end of round 1, all the party will have some value assigned to their level 1 nodes of local EIG trees. We will see how. So now P1, okay, P1 has value 1 at its node with level lambda, right? P1 has value 1 at its node with level lambda, that is root node. P1 will send this information to all the parties including itself. So P1 will send the information, this information lambda comma 1, which means P1 is saying that see, my root node, because lambda denotes the root node only, so, or in other words, P1 says that at my EIG tree, the value at node with level lambda is 1, right? Or the node with level lambda contains the value 1 in my EIG tree. That is what P1 is saying to all the parties including itself. So P1 sends this information to all, P1, P2, P3, P4. Okay, send. What P2 sends? P2 has value 0 at its node with level lambda. So this information will be sent to P1, P2, P3, P4. Okay. P3 has value 0 at its lambda node. This will also send this information to all the parties. Okay. And P4, here comes the fun actually, because P4 is corrupted. So it is actually supposed to send lambda comma 1 since it has 1 at its root node, but it may choose to send some different values as well. So let's say it sends lambda comma 1, the actual value, to P1, sends lambda comma 0 to P2. So this is arbitrary behavior. Lambda comma 1 to P3, again lambda comma 0 to P4. Just arbitrary behavior. Okay. So honest parties will always send the same value to all the other parties. They will not lie, but P4 can lie about its value arbitrarily to other parties. So this is the send part of the protocol, and as well as also receive of the values are also done. So P1 has received lambda comma 1 from P1, P1 has received lambda comma 0 from P2, P1 has received lambda comma 0 from P3, and P1 has received lambda comma 1 from P4. So send and receive operations are done. Now assignment. How the parties P1, P2, P3 and P4 will assign values to their nodes of level 1 at their respective EIG tree. So now I am going to fill up these 4 columns, right? Level 1, denoting the level 1 nodes of all the parties EIG trees that I am now going to assign values. So what we will do? So P1 sees that it has received lambda comma 1 from P1. That means it will assign the value 1, right? This value 1 to the node having label lambda concatenated with the party ID 1. I am repeating it again. P1 has received lambda comma 1 from P1. So this value 1 will be assigned to a node that has label lambda concatenated with this party ID 1. So lambda is just an empty string, so lambda concatenated with 1 is nothing but 1. So value 1 will be assigned to node with label 1 of P1. So in P1's EIG tree, the node with label 1 will have the value 1. Next, P1 has received lambda comma 0 from P2. So P1 will assign the value 0 to the node with label lambda concatenated with party ID 2. That means this value 0 will be assigned to a node having label lambda concatenated with 2, and lambda concatenated with 2 is nothing but 2. Next, again P1 has received lambda comma 0 from P3. So this value 0 will be assigned to a node having label or tag lambda concatenated with party ID 3. So lambda concatenated with party ID 3 is nothing but 3. So P1 assigns value 0 to the node with tag 3. P1 has received lambda comma 1 from P4. So it will assign value 1 to the node with tag lambda concatenated with 4. So it will populate the node with label 4 with value 1. I hope I am clear. Now analogously, let us fill the level 1 nodes for P2's EIG tree. So what P2 has received? P2 has received lambda comma 1 from P1. So P2 will fill the value 1 at the node labeled with or tagged with lambda concatenated with party ID 1. So the node with tag 1 will have the value 1. P2 receives lambda comma 0 from P2. That means the node with tag lambda concatenated with 2 or 2 will have the value 0. So for P2's EIG tree, the node with label 2 or tag 2 will have the value 0. P2 receives lambda comma 0 from P3. So P2 will assign value 0 to the node with tag 3. P2 receives lambda comma 0 from P4. So it will populate value 0 to the node with label 4. Okay. What about P3? So P3 receives lambda comma 1 from P1. So it will assign value 1 to the node with label 1. P3 receives lambda comma 0 from P2. So it will assign value 0 to the node with label 2. P3 receives lambda comma 0 from P3. So it will assign value 0 to the node with label 3. And P3 receives lambda comma 1 from P4. So it will assign value 1 to the node with label 4. Coming to P4, P4 receives lambda comma 1 from P1. So it assigns value 1 to the node with tag 1. P4 receives lambda comma 0 from P2. So it assigns value 0 to the node with tag 2. P4 receives lambda comma 0 from P3. So it assigns value 0 to node with tag 3. And P4 receives lambda comma 0 from P4. So it assigns value 0 to the node with tag 4. So now our level 1 assignments have been done. Okay, so round 1 is now completed. I hope till this point it is clear to you. Okay. Now I will start with again round 2, right? So assignment is sent is done, receiving is done, and accordingly assignment to level 1 nodes of individual EIG tree is also done. Now we start round 2. Again it will have its own sent, receive and assign. Now in round 2, what information P1 has in its local EIG tree at level 1? So P1 has value P1 at its node with tag 1 has value 1. Its node with tag 2 has value 0. Node with tag 3 has value 0. Node with tag 4 has value 1. This is the level 1 information that P1 has. Now since this particular information has the node with level 1, so in this tag its own party ID is present, right? 1 is its own party ID. So since the label contains its own party ID, this particular information is not needed to be sent. So it does not send this information. But for rest of the node tag, the information will be sent. So all these informations actually will be sent to all the parties. Again, P1, P2, P3 and P4. Okay, P1 has sent these 3 values to all the parties. What about P2? Similarly, P2 will have information value 1 at label 1 or tag 1, value 0 at tag 2, but since the tag 2 contains its own party ID, so it will not send that information. Next information is value 0 at node tag 3, so 3, 0 and then 4, 0, right? All these information will be sent to all the parties including itself. What about P3? P3 will send value 1 at node tag 1, value 0 it has value 0 at node label 2 or node tag 2, value 0 at node label 3, but since this label 3 contains the party ID 3 itself, so it will not send this information. It will send value 1 for node label or node tag 1, right? All these informations are sent to all the parties. Next comes P4. So remember that P4 is the adversary, right? Or P4 is the corrupted party. Here also just let me cover it with red so that you can point out that it can behave arbitrarily, and everyone, right, will have its own input, right? Just let me just charge my laptop. Just give me 1 minute. Sorry for the interruption. Coming back, yes, so we were telling that P4 is the corrupt party, so it can behave arbitrarily. That's why I just made it highlighted with red so that you can see that it has sent different values to different parties. Now, so just here also, this is the corrupted party, so it can behave arbitrarily. Now, what information P4 has in its EIG tree at level 1? At level 1, it has value 1 at node tag 1, right? So they are actual value of its node. So value 0 at node label or node tag 2, and value 0 at node label 3. Node label 4 or node tag 4 contains its own party ID, so that is not the information that it will send. Anyway, so let's say this is the value it sends to P1, but it may not send the same value to everyone, so just randomly assume that it sends this to P2, and I am arbitrarily changing the values, right? So let's say this to P3 and this to P4, this to itself, right? Now the sent and received part is done for round 2. Okay, now comes the assignment part. So each party will now assign values to its local EIG trees nodes at level 2 L equal to 2. These nodes will be now populated. How? Using the same rule actually. So we see that P1 has received all these values from P1. So receiving value 2, 0 from P1 implies assigning value 0 to the node at Pij's local EIG tree with tag 2 concatenated with this party ID 1. That is, the node with tag 2, 1 or label 2, 1 will receive the value 0. So let us populate that P1 will assign value 0 to the node with tag 2 concatenated with party ID 1. So 2, 1, node tag 2, 1 will receive value 0. Again, P1 also receives 3, 0 from P1. That means value 0 will be assigned to the node with tag 3 concatenated with 1. So 3, 1 will receive the value 0. Node with tag 4 concatenated with 1 will receive the value 1. So node 4, 1 will receive the value 1. Next, what P1 receives from P2? P1 receives 1, 1, 3, 0 and 4, 0 from P2. That implies that value 1 will be assigned to the node with tag or label 1 concatenated with 2. Right? So 1 concatenated with 2 means the node with label 1, 2. That will receive this value 1. So node 1, 2 will receive the value 1. Similarly, node 3, 2 will receive the value 0. 3, 2 will receive the value 0 and node 4, 2 will receive the value 0. Next, P1 receives 1, 1 from P3. So node with label 1, 3 will receive the value 1. So 1, 3 will receive the value 1. 2, 3 will receive the value 0. 4, 3 will receive the value 1. Coming to last part, P1 receives 1, 1, 2, 0, 3, 0 from P4. So in the view of P1, so it assigns value 1 to its EIG tree's node with label 1, 4. Right? So 1, 4 will assign the value 1. 2, 4 will be assigned the value 0. 3, 4 will be assigned the value 0. Now, party P1 has allocated some values to all its level 2 nodes. Similarly, party P2 will also assign the values. So P2 will receive, or P2 has received from P1 2, 0, 3, 0, 4, 1. Okay. That means node with label 2, 1 has received value 0. 2, 1 has received value 0. 3, 1 has received value 0. 4, 1 has received value 1. Okay. Similarly, in this case, node 1, 2 will have the value 1. 3, 2 will have the value 0. 4, 2 will have the value 0. For P3, coming here, P2 received 1, 1, 2, 0, 4, 1 from P3. So P2 will assign value 1 to node with label 1, 3. 1, 3 gets the value 1. 2, 3 gets the value 0. 4, 3 gets the value 1. Similarly, in this case, 1, 4 gets the value 0. 2 4 gets the value 1. 3 4 gets the value 1. Now what about P3? So P3 receives again 2, 0, 3, 0, 4, 1 from 1. So node 2 1 gets 0, 3 1 gets 0, 4 1 gets 1. From here node 1 2 gets 1, 3 2 gets 0, and 4 2 gets 0. From here 1 3 gets 1, 2 3 gets 0, 4 3 gets 1. From here 1 4 gets 1, 2 4 gets 1, 3 4 gets 1. For P4, starting from here, 2 1 gets 0, 3 1 gets 0, 4 1 gets 1, 1 2 gets 1, 3 2 gets 0, 4 2 gets 0, and here 1 3 gets 1, 2 3 gets 0, 4 3 gets 1, and here 1 4 gets 1, 2 4 gets 0, 3 4 gets 0. Now one thing you should notice is that you can notice that P4 is the corrupted party, right? So at label 1 you can see that all the columns except the column having label or tag 4 has the same values throughout all rows, right? So this column is corresponding to node tag 1. So for all the local EIG copies, right, all the local EIG copies for all parties have the same value at node with label or tag 1. Same is the case for node label 2, node label 3, but for node label 4, P4 being the corrupted party, all the contents of this column are not consistent, right? So it basically signifies the fact that whatever, so this node signifies that P4 tells P1 that my root node entry is 1. This entry signifies P4 tells P2 that my root node entry is 0. This signifies that P4 tells P3 my root node entry is 1, and again P4 tells P4 itself that my root node is 0. So basically P4 is lying to everyone. Its message is not consistent to all the parties. That's why these entries are different in this column. Whereas P3 being an honest party, it sends everyone the value 0. So looking at this tree, this communication, you can see that P3 is communicating the value 0 to everyone. That actually corresponds to this column, that P3 has told P1, P2, P3, P4, everyone that my root node value is 0. Whereas P4 has told P1 that my root node entry is 1. Here it has said that my root node entry is 0. To P3 it has said that my root node entry is 1. And to P4 it has said that my root node entry is 0. So it has lied to everyone. That's why this column entry is not consistent. Similarly, the node label 1 2, the particular label or tag 1 2 does not involve the corrupt party ID 4. So all the entries in this column are consistent. Same is the case for 1 3. Whereas for 1 4, since the last ID, party ID is corrupted, so this last party ID is 4 means the last communication was done by a corrupt party P4. Since P4 lies to everyone, or whatever P4 says is not consistent through all the parties, that's why the column entry is not consistent. So the label 1 4 has value 1 for P1. So this signifies that at round 2, P4 has told P1 that at round 1, P1 has told P1 that my root node entry is 1. Whereas here P4 has told P2 that P1 has told P2 that its root node entry is 0. That is reflected here. Coming to last row, here P4 has told P4 at round 2, P4 has told P4 that P1 has told P4 that its root node entry is 1. Okay. So this particular column, having the last node as the corrupted part, having the last entry in its label being a corrupted party ID, the column entries are inconsistent. Same is the case for this column and this column. For the rest of the columns, you can see that all the entries are actually consistent throughout the rows. Okay. Anyway, now you can see that after the termination of round 2, all the parties have already filled up their respective EIG trees, right? This tree structure is filled up with some values for all the parties. Now, what will be the final output decision? So here only let me write actually using some other color maybe. So let me use this. Okay. So output decision is done in this manner, that every party will take a bottom-up approach. So it will assign some new values to all the entries of its EIG tree, right? So new value of the leaf nodes will be same as the old value of the leaf nodes. So all these leaf nodes value, that is level 2 values, they will be unchanged. Okay, they will be unchanged. Now new value will be assigned to level 1. How? Basically, each node at level 1 will be assigned the value which is majority value of its children. So the values at node tag 1 2 1 3 1 4, whichever has a majority count, will be, that value will be assigned to node tag 1. Similarly, the majority value of the values present in node tag 2 1 2 3 2 4 will be assigned to the node tag 2. So if I just denote here, so 1 2 1 3 1 4, majority of these 3 entries will rewrite the content of this node, right? Majority of these 3 columns will actually write to this node, right? Pardon me for this. Okay. 3, 1, 3, 2, 3, 4. These three will actually go to this column. You can understand I am not drawing that line. And 4, 1, 4, 2, 4, 3, they will affect the value at this column. Okay. So let us just check for P1's EIG tree first. So 4, 1, 4, 2, 4, 3 has majority value 1. 1, 0, 1. Which one is the majority value? 1. So that value should be assigned to node with tag 4. So it is already 1, so no need to change. 0, 0, 0. 3, 1, 3, 2, 3, 4. So the majority value is already 0 and this value is also 0. So no need to change. 2, 1, 2, 3, 2, 4. All the values are 0. So the majority value is 0 and this value is also 0. So no need to change. 1, 2, 1, 3, 1, 4. All the values are 1. So it is already 1. So no need to change. Okay. Now for the root node, again now this is level 1 thing that is done. So after the new value assignment of level 1, all the values are unchanged for P1, but then majority of all the level 1 nodes will be the value at the final value at the root node. And in case no majority is found, like in this case we can see that 1, 2, 3, 4 they contains 1, 0, 0, 1. So neither 0 nor 1 is a major has a majority count. So in that case we will assign some default value to the parent node, right? Let's assume that default value is 1. Okay, just assumption. So in that case the default value 1 will be assigned to root node, and since this node has already value 1, so no need to rewrite as well. Okay, so P1 has already got its output to be 1. This is the final output of P1. P2 will also run the same bottom up approach to get some value at its root node. So let's see. 4, 1, 4, 2, 4, 3, 1, 0, 1. The majority is 1. So the value at node 4 should be 1. So we will rewrite this value as 1. 3, 2, 3, 4. 3, 1, 3, 2, 3, 4. 0, 0, 1. So majority count is 0. So node 3 will have the value 0. It's already 0. No need to rewrite. 2, 1, 2, 3, 3, 4 has the majority value 0. And this is already 0. That's okay. And 1, 2, 1, 3, 1, 4. 1, 1, 0. So majority count is 1. This is already 1. So it's okay. Now the majority of all the level 1 nodes, that is 1, 0, 0, 1. So no one has a majority count. So the default value 1 will be assigned to the root node. So this is the final Byzantine agreement output for P2. For P3, again 1, 0, 1, majority is 1. So this should be 1. Okay. 3, 1, 3, 2, 3, 4, 0, 0, 1. Majority count is 0. This is already 0. 2, 1, 2, 3, 3, 4, 0, 0, 1. Majority count is 0, which is already 0. And 1, 2, 1, 3, 1, 4. Majority count is 1. This is already 1. So nothing is changed. And since there is no majority over the level 1 nodes, we will assign default value 1 to the root node, and this is the final output of P3 after the Byzantine agreement protocol. For P4, again taking the bottom up approach, 1, 0, 1, majority is 1. So this value will be rewritten as 1. 0, 0, 0, majority is 0. This is already 0. 2 1 2 3 3 4 all 0, so majority is 0, this is already 0. 1 2 1 3 1 4 1 1 1, majority is 1, this is already 1, no need to change. Now among these level 1 note 1 0 0 1, so no one has a majority count, so they will have the default value 1, so this is already 1. So you can see at the end of the Byzantine agreement protocol, now the protocol is finished, everyone has got some value at their root node, and that is the output for their Byzantine agreement protocol, and you can see that everyone has agreed upon actually one particular value, which is 1, right? And since at the beginning of the protocol it is not the case that all the honest party had the same input at the beginning of the protocol, so we do not see that some particular, let's say if P1 would have started the Byzantine agreement protocol with input 0, and P2 and P3, so P1 P2 P3 all three honest party, if they would have started the protocol with value 0, then we should expect the Byzantine agreement protocol output to be 0 for all the honest party, but that is not the case here. All the honest party had some different outputs at the beginning of the protocol, but still at the end of the protocol all the honest party have agreed upon the value 1 at the end of the protocol, right? So that is the output of Byzantine agreement protocol. I hope the protocol demonstration is clear to you. Now one interesting fact to observe is that looking at so let me just copy P1's EIG tree content before the assignment of new values, okay, and get some interpretation for that. So I am going to next slide and we will copy the PIG trees content there, okay. So let's draw EIG tree for party P1, okay. And we will try to have some interpretation from that. So what were the contents? I am writing from here. So root node has 1 and the next level node has 1 0 0 1, okay. So the contents are 1 1, okay, let me write it using some other ink. This is value 1 0 0 1 and 1 2 1 3 1 4, right? So this is 1 1 1 0 0 0 0 0 0 1 0 1, right? So 1 1 1 0 0 0 0 0 0 1 0 1, that is the EIG tree value, right? Now let's say you don't know that it is P1's EIG tree, right? I'll just write the label of the nodes as well, or tab of the nodes with different ink. So let's say, this is the label of the nodes 1 2 3 4 1 2 1 3 1 4 2 1 4, 3 1, 3 2, 3 4, 4 1, 4 2, 4 3. They are the tags, and inside in yellow color the values. Now you don't know that this is P1 CIG tree. You just know this is some honest party PI's EIG tree, where of course I can be anything between 1 2 3 4, and you have to determine that which is the corrupt party by looking at the EIG tree of some honest party PI. So essentially what we try to determine here is that which party is lying at some step. So let us just analyze. Okay. So from the EIG tree we can see that PI has PI has 1 at its root node, that is its initial value is 1, right? Then in round 1 from the EIG tree we can say that P1 has told PI that its root node has value 1, right? P1 has told PI, from this value we can say that P1 has told PI that its root node value is 1. That is why it has assigned 1 to its node with tag 1, right? What else? P2 has told PI that its root node value is 0. P3 has told PI that its root node value is 0, and P4 has told PI, we don't know what PI is, but from the EIG tree we can say that P4 has said PI that my root node value is 1. So any one of them can be lying, okay, like at most one of them will be lying. So this is the occurrence at round 1, and then in round 2 from this we can say that P2 has told PI, right? Since the last ID of the tag is 2, so P2 has told PI that P1 told me that means P1 told P2 that its root node value is 1. Okay, P2 tells PI that in previous round P1 told me that P1's root node value is 1. That is implied by this node's value. What does the value in this node imply? This implies, so the node label or node tag is P3. So P3 has told PI that in previous round P1 told P3 that P1's root node value is 1. Okay. Also P4 tells PI that P1 in previous round told P4 that its root node value is 1, right? From this node we can say. Till now this looks fine because everyone claims, P2 also claims that P1 sent 1 to him, P3 also says that P1 sent 1 to him, P4 also said that P1 sent 1 to him in round 1, and also in round 1 PI itself got 1 from P1. So P1 seems to be a honest party. It did not lie because everyone's claim is that P1 had sent 1 as its root node value to everyone. Till now all okay. So you need to find some liar in this scenario. Okay. Next, you can see that from this node we can say that P1 has said Pi that P2 told me that P2 told P1 that its root node value is 0. Okay. Next, P3 told Pi in round 2 that P2 in round 1 told it that its value, root node value is 0. And P4 tells Pi in round 2 that P2 in round 1 told it that its root node value is 0. Again, till now everything seems okay, and P2 seems to be a honest party because everyone's claim is that in round 1 P1, P2, P3, P4 everyone says that P2 sent 0 to it in round 1. Okay. What about here? Here from this node I am telling P1 tells Pi that P3 told it in P3 told P1 in round 1 that its initial value is 0. P2 tells Pi that P3 told P2 that its initial value is 0 from this point, and P4 tells Pi that P3 told P4 that P3's initial content is 0. Still it seems okay, right? Because everyone says that in round 1 P3 told its value to be 0. No lie found till this point, right? Okay. Now coming to here. Here P1 tells Pi that P4 sent P1 a value 1 in round 1. P2 says to Pi that P4 sent P2 value 0 as its initial value. Now you find some lie here, because at round 1 Pi received 1 from P4 as its root node value. So P4 claimed that my root node value is 1 to Pi in round 1, and in round 2 P1 is telling Pi P1 is also telling Pi that in round 1 P4 told me that its initial value is 1, but P2 is telling Pi that in round 1 P4 told me that its initial value is 0. So there is this mismatch, right? So P4 apparently told P1 that its value is 1, P4 told P2 that its value is 0. So P4 seems to be the potential liar or the corrupt party. Looking at the last node, here P3 tells Pi that P4 told P3 that its initial root node is 1. So basically P4 tells P1 that its initial value is 1, P4 tells P2 that initial value is 0, and P4 tells P3 that its initial value is 1. So here P4 turns out to be a liar basically. So right, so this is the mismatch, and P4 turns out to be a liar. So by looking at the EIG tree of some honest party PI, you can uh, you can essentially derive that which one is the corrupt party in this scenario. You can try on yourself by looking at EIG tree of some other honest party, say P2 or P3, and try to find out which one is the corrupt party by looking at their EIG tree. Similarly, by looking at EIG tree, you might also find out that whose EIG tree it is, right? By looking at the entries of the EIG tree, and the entries are before the new value reassignment to the nodes. Okay. So I hope I made the EIG tree construction clear to you, and I hope it helps you in better understanding the protocols and answering the weekly assignment questions. Okay. So thank you for joining or watching the tutorial session. I will end the session here. Thank you. Next week we will discuss the assignments. Actually.